Hello all, welcome to this online recording sessions in data science. So in this session, we are going to see some of the CNN architectures, convolution neural network architectures, and then followed by object detection models of deep learning, then followed by object detection models, measurable parameters. Okay, so now let us see the convolution neural network architectures. So how they are. So they are mostly 4 to 5. So here you can see LNet, AlexNet, VGGNet, GoogleNet, ResNet. So all these 5 deep learning convolution neural network architecture, we are going to see their architecture and their features one by one. Okay. So first LNet. So LNet 5. So LNet 5, what is the specialty of this LNet 5 architecture? You could see tanh activation function is used in the original LNet 5 architecture. Okay. Then ReLU activation function is used to improve the performance a bit. So these two activation functions are used in LNet 5. So apart from this, so we have convolution neural networks, pooling layers, and then followed by some layers, some flattening layers and all. So we will be seeing all those things in the architecture. So before that, so let us see in which paper it was invented and the author of this invention also. Let us see. So LNet 5 was proposed by famous AI pioneer N. Lucin. Okay, so he is the founder of this LNet 5 architecture, and it was proposed in this research paper. Okay, gradient based learning applied of document recognition. So in this research paper, this LNet 5 architecture, CNN architecture was proposed. Okay, so we have seen in which paper it was found and who is the founder of this architecture. Okay, so now let us see these steps one by one in the architecture. Okay, yeah, this is LNet 5 architecture. If you see how many convolution neural network has, it has 2 convolution layers. It has 2 convolution layers, and it has 2 pooling layers. 2 pooling layers, and then followed by fully connected layers. Okay, so you can see the 2 convolution layers are here and here. So these are the 2 convolution layers that are present. Okay, and those are 16. Okay, and they are 5 cross 5 and they are in number of 16. Okay, the first one is with 6 convolutions and the second one is 16 convolutions. Okay, so with the padding size of 2 here in the first case, and in the second case there is no padding, we are just giving 5 cross 5 and the convolutions are 16. Okay, and the pooling size is 2 cross 2. So here the image is passed, then followed by these 3 layers. Okay, so top you could see this fully connected layers. The first fully connected layer is with 120 layers, then followed by 84, then followed by 10. Okay, so this is the architecture of LNet 5. Okay, so you could see this is mostly designed for the handwritten digit recognition. Okay, so we have 0 to 9 digits. So for this handwritten digit recognition problem, this architecture was designed, okay, to study that. Okay, next architecture was AlexNet. Okay, so AlexNet architecture. So what is this? Who invented this? So it was designed in 2012 by Hinton and colleagues, and it won ImageNet large scale visual recognition challenge in 2012. Okay, so that we can call it as ILSVRC also. Okay, so it overcome this challenge. Okay, this challenge is the standard to evaluate image classification problem. Okay, so this ILSVRC challenge is used to overcome the image classification problem. Okay, it is very larger than the previous architecture, that is LNet 5. Okay, and then you could see the layers are also increasing. The convolution layers are increasing, the pooling layers are also increasing. So I think there are 5 convolution layers. Okay, 1, 2, 3, 4, 5. So 5 convolution layers and 3 pooling layers, and then followed by 3 fully connected layers. Okay, so how many fully connected layers? 3 are there, right? So 3, the first fully connected layer with 4096 layers. Okay, then next also 4096 layers, then followed by 1000 fully connected layers. So okay, all these parameters are, you could see, first 11 convolution layer with 96 layers. Okay, with a stride of 4. Okay, stride, padding, pooling, and all those we have seen in the other session, right? CNN. Okay, so this is image that we are giving, and then this image is entering into this architecture, where you could see all these layers: 5 convolution layers, 3 pooling layers, and 3 fully connected layers. Okay, so in this the main advantage is we are using dropout. Okay, dropout to overcome overfitting challenges. Okay, so it removes the effect of some neurons that are not necessary. Okay, using this technique. And this data set was designed with the different ImageNet dataset. So the dataset name that we have taken for this architecture is ImageNet dataset. Okay, to train. So previously LNet we have taken handwritten digit recognition dataset. For this AlexNet architecture we are taking ImageNet dataset. Okay. So next, VGGNet. Okay, so VGGNet is one of the most important CNN architecture. Okay, so here there are subcategories also: VGG16, VGG19. So all those are there, and it is mostly used nowadays. Okay, so and it was proposed in 2014 by Visual Geometry Group at Oxford University. Okay, it showed deep architecture led to better results of convolution neural networks. Okay, so it consists of 16 convolution layers with 3 cross 3. Okay, so you could see 16 convolution layers. Okay, here you can see 16 convolution. So 2, right? So 2 plus 4 convolutions, plus followed by 4 convolutions, followed by 4 convolutions. So total 14, 4, 8, 12, 16. Yeah, one more 2 I need to add. So this also. Okay, so total we have 16 convolutions. So 16 convolutions. So you could see the difference. LNet 5 and AlexNet are slightly modified, and it looks somewhat different than those two architectures, if you ask me. Okay, so you could see here 2 into it has taken, that means 2 convolutions are present here. So that is the difference between those two and this one. Okay, then followed by pooling layer. So how many pooling layers? Okay, so it is consisting of 16 convolutions with 3 cross 3 filter. Okay, with 3 cross 3 filter. Okay, then it is also having, it is trained on the ImageNet dataset. So AlexNet is also trained on ImageNet dataset, and this VGGNet also trained on ImageNet dataset. Okay, and this VGGNet is capable of predicting 1000 different classes in ImageNet dataset. Okay, so this got trained on 1000 different classes. Okay, not 2 or 3 or like that. 1000 different classes of in ImageNet dataset. Okay, so and it is able to predict those 1000 also. Okay, so yes, and so you could see the max pooling layers also. So 1, 2, 3, 4, 5. So 5 max pooling layers. Okay, pooling layers, and 2 fully connected layers. fully connected layers. Okay, so you could see all these three features in the architecture of VGG net. Okay, so and this VGG net is further divided, or the variants of VGG net are VGG 16, okay, and VGG 19. Okay, so these are the variants of VGG net. Okay, I hope you understood, right? And it is mostly used. It is trained on ImageNet dataset. Okay. Okay. Now next, let us see one more architecture. Okay, one more architecture, that is ResNet. ResNet, I think. Okay, not ResNet. We will see later. We will see Inception Net. Okay, what is this Inception Net? Okay, it was proposed in. It is also proposed in 2014. The very first Inception Net, we call it as Google Net. Okay, the very first version of Inception Net, we can call it as Google Net. Okay, you can see here. The idea is to introduce filters of multiple sizes. Okay, that can operate on same levels. So here we are trying to use filters. So when you compare with the remaining architectures, here you are using filters. Okay, so if a network having lot of layers, then there is a chance that it can suffer from problem of overfitting. Okay, so in AlexNet we have used dropout, right? So here also we use some other technique. Okay, so we use ILSVRC, ImageNet Large Scale Visual Recognition Challenge. Okay, okay, we use this. Okay, which evaluates algorithm for image classification and object detection. Okay, ILVRC. Okay, we use this. So here you could see the architecture. If you want me to talk about the architecture, so it has got one cross one convolutions. So all together there are three convolutions, three convolution layers. Okay, and one pooling layer, that is max pool. Okay, max pooling. So three convolutions, and those are different, not similar one. Okay, so one is 1 cross 1 convolution, the other one is 3 cross 3 convolution, the other one is 5 cross 5 convolutions. Okay, followed by 3 cross 3 max pooling. Okay, whole architecture is referred to as Inception module. Okay, so this is all about Inception Net. The very first version of Inception Net is Google Net. Okay, okay, then next we will see in detail about this Inception Net. Okay, yeah, yeah, I think these architectures are different. No, right? Okay, Google Net architecture. Okay, it is 22 layer deep, consisting of 27 layers. There are total of 9 inception modules. Okay, there are total 9. You can count. Okay, 1 2 3 4 5 6 7 8 9. Okay, so there are total 9 inception modules which are stacked linear. Okay, so at most weights in convolution neural network are found fully connected. Okay, so it also uses ReLU activation function when compared to that AlexNet, sorry, Inception Net. So here in Google Net we use ReLU activation function. So here, if you want me to talk about this architecture, so we have 1 cross 1 convolution layer. So total how many convolutions we have? 1 2 3 4 5 6. So 6 convolutions, 6 convolution layers, and one pooling layer. Okay, okay, so one convolution layer before 3 cross 3. So this is slightly modified. Yeah, you see 1 cross 1 convolution is present here also. 3 cross 3, 5 cross 5 are also present here. Okay, they are present here, but to that version, that is the first version. That's why we are calling it, labeling it as Google Net. So On top of that, we are adding this one, this convolutions extra in this architecture. Okay, so that is the difference, main difference between Inception net, okay, and Google net. So we are adding extra convolution layers, 5x5 convolution. Okay, so that is the main difference between Inception net and Google net. We are adding extra layers, and here also Rayleigh activation function is used. Okay, yeah, the next last architecture of in CNN is RESTnet. So here you can see, so what here you could be skipping concept is used here. So in RESTnet we are using skipping concept, okay, or we can call skip connections. So it solves the problems of vanishing gradient problem. Okay, that is so that comes in the deep learning. So vanishing gradient problem can be overcome using RESTnet. Okay, in addition to normal connection, it introduces additional connection which skips some layers. So if you observe all the architectures of previous ones and this one, there are so many layers that got skipped, right? So there are so many layers that got skipped, and it that's why it is called as skip connection. So whenever there are unnecessary layers or unnecessary connections, those are skipped automatically in this architecture. Okay, while using this architecture, you need to remember the unnecessary or unused layers are skipped, and the used layers are only taken into consideration, and then the processing takes place. Okay, so next we are going to see object detection models. So in this object detection models, we will see there are two types. There are two types of object detection models. So the very first one is single stage object detection, and the other one is two stage object detectors. Okay, in single stage object detectors, we will see RCNN, faster RCNN. Okay, so there is some little bit difference between these three. We are going to see in single stage detector, we will see YOLO. Okay, so what is this object detection? So what they used to do and where they are used. So these object detection models are basically used for pointing out a particular object in a group of image. Okay, so in a crowd, so in a group photo, or in any group activity, we can point out some particular object. Okay, so that is why we are calling object detection models. Okay, so we have many applications of this object detection models: car detection, vehicle detection, person detection. So all those are comes in object detection. Okay, so why these two stage detectors and single stage detector? So in two stage detectors, what happens? The process will takes place in two ways. Though in first stage, we'll identify the objects. Okay, so we have an image. Okay, we will be having an image. So in that image, we will extract. We'll form the layers. That means we'll identify the objects. Then in second stage, what we'll see, we'll try to plot a bounding boxes. Okay, so these are the two steps that are involved in two stage detectors. In single stage detector, altogether these two things will happen at the same time. That's why we are calling it a single stage detector. Okay, so that is the difference between single stage detector and two stage detector. And in single stage detector, you could see YOLO. Nowadays most people are using, okay, for object detection. So generally when you are studying about computer vision concepts, I think it will be helpful. These all are related to deep learning detectors, object detectors. Okay, and this is a special type of detector, that is YOLO, and it is single state detector. Okay, so we are going to see one by one in this session. Okay, in the coming slides we are going to see one by one. So the very first one is RCNN. Okay, in RCNN, so RCNN stands for region based convolution neural network, and it was proposed in 2014. Okay, and it was proposed by this author, okay, Rich Sick. Okay, and in this paper it was found. Okay, so what does this RNN consist of? It consists of three modules. The one is region proposal. Okay, region proposal. The other one is feature extractor. The other one is classifier. So what these three regions will do? The first region proposal will generate candidate bounding boxes from an image. So I have this an image, right? So what does this is a two-stage detector, right? First, what it will do? It will identify the objects from the image. So what are the objects? So this person is one object, this horse is one object, and you could see something is here. Okay, so that is also, it is identified as one object. Okay, it may not be correct, but you try to understand the concept. This model is trying to identify the objects from the original image. Okay, so it has identified. So in this the very first region proposal layer, then in next step, what it is doing? Feature extractor. So it is trying to extract features. That means it is trying to identify. So what features? Eyes, nose, head. So what kind of category it comes? So this is an object, right? So in this object, in next stage, the features are getting identified. Okay, so how it is looking, and then we will classify it. What kind of object it is, we will be classifying it in the next stage. Okay, so in features we are trying to see the features of that object and then try to classify. If an object is having eyes, nose, ears, hair, and similar to a human, then we can classify it as human, right? So like that, it will identify features. Okay, person. Otherwise, it is no means some other, it is looking like an aeroplane or like that, it is predictive. Okay, so this here you could see here a selective search algorithm was used, and algorithm selective search was proposed to find candidate bounding boxes. So to find these bounding boxes, we are using selective search. Okay, the extracted features are then fed to SVM. So these extracted features are fed to SVM. So internally, these steps are also getting added. So to what I was trying to convey is, so you understood this concept, right? So internally, these extracted features are passed to SVM for the classification of the object. So SVM does this classification. Okay. So there is a drawback of this also. The drawback of RCN is that it is very slow. Okay, it requires feature extraction, a lot of bounding boxes. So it requires a lot of features, and sometimes it will identify wrong objects also. That is also one drawback of this RCNN. So that's why we'll go to the another model, that is fast RCNN. Okay, fast RCNN. So in that we will see what is the difference. So in this, what we are trying to do, we are trying to overcome the drawbacks of RCNN. Okay, and this is invented in 2015 in the paper fast RCNN. Okay, so these are the drawbacks of RCNN. So that drawbacks are overcome in this fast RCNN. Okay, what are those drawbacks? Training in multiple stage. Okay, there are different stages in RCNN. So in that different stages, the training is different. Okay, and training is also expensive and time taking. Okay, so that is why sometimes the third one also, I think I have not mentioned, classification is also wrong. Okay, so these three are drawbacks of RCNN. So to overcome all these drawbacks, we are trying to see fast RCNN. Okay, so in fast RCNN you see only the single object is detected. Okay, so you compare. So there how many objects are got detected, and here how many objects are got detected. Okay, and what is the difference? So what algorithm is different from here? So the difference is spatial pyramid pooling networks. Spatial pyramid pooling networks. Okay, so we are using spatial pyramid pooling networks to speed up RCNN. Okay, so we are using this technique to overcome the drawbacks of RCNN. Okay, so the authors of RCNN only developed this fast RCNN. Okay, okay. So next we will see faster RCNN. So what is the advantages of faster RCNN? We have seen RCNN, fast RCNN. Now we will see faster RCNN. So in faster RCNN, so we will be adding one more extra layer. That's it. So RPN. RPN concept comes in faster RCN. Okay. So remaining layers are similar to faster RCN. So what is this RPNN? Okay. So RPNN is convolution neural network for proposing the regions and the type of class to consider. Okay. So this RPN will identify the regions correctly. Okay. This will help in identifying the regions correctly. Okay. It outputs a convolution neural network for proposing the regions and the type of class to consider. So which class to consider and all, this RPN is decided. Okay, so that is the difference between fast RCNN and faster RCN. RPN concept is added. Okay, in between. So in those layer in between we are adding this concept. Okay, so and you can see in which year, in 2016 it was invented, and in which paper. In the paper faster RCNN towards real-time object detection using region proposal network. So in this paper this faster RCNN concept was introduced. Okay, it provides speed, accuracy, and faster. It works faster than RCNN and fast RCNN. Okay, this architecture proposed to both refine region proposals as part of training process referred to as region. Yeah, that is what it is talking about RPN. Okay, used to combination with fast RCNN. So this RPN concept is added to faster RCNN. So that is the difference. That is the only difference if you ask me. So remaining thing, everything will be similar. Okay, so we have classifier, ROI pooling, and feature maps, convolution layers, which is similar to fast RCNN. Yeah, that's all about the two-state detectors. Then we'll come to single state detectors. So in single state detector, YOLO is the one of the popular algorithm that is used, and this is introduced by Ultralytics. Okay, so Ultralytics company designed this YOLO. Okay, so we have versions like YOLO 3, YOLO 5. I think the latest version is YOLO 12, most used. Okay, YOLO 12, YOLO 14, YOLO 15 also came, I think. We need to check it. Okay, so Ultralytics company provides all these algorithms. So you can just extract from Ultralytics website this YOLO algorithm and try to use it for detecting objects. Okay, so YOLO stands for you only look once. So okay, and it was proposed in 2016 in the paper You Only Look Once, Unified Real-Time Object Detection. Okay, so it makes usage of neural network which is trained end to end, that makes an image as input and predicts bounding boxes and class labels directly. So like I mentioned, two-stage detector, first identifying the objects, then trying to draw the bounding boxes, right? But here you can see it will directly identify the in one stage only it is trying to identify bounding boxes, and to that bounding boxes it is trying to it is trying to it is trying to segregate the real objects from that. Okay, so all those two steps are happening in single step only, so that's why we are calling it single stage object detectors. Okay, so YOLO 9000 was proposed in the paper YOLO 9000, so which is better, faster and stronger. So YOLO 9000 is also there. Okay, apart from YOLO 3, YOLO 5, YOLO 11, YOLO 12 and all, YOLO 9000 is also there, so you can check that also. Okay, so you can go to Ultralytics website, you can find all this, and they'll be giving some real life examples also to study. So to apply all, how to apply step by step procedure, they'll mention in their website. Okay, you can go to that Ultralytic website. Okay, so next we are going to see evaluation measures for object detections. So we have seen what is object detection, right? So how far those objects are detected, the detected objects are, how far they are good. Okay, how good they are, how bad they are. So all those can be measured using some evaluation measures. Okay, so we are going to see that evaluation measures for object detection. The first one is IOU, intersection over union technique. Okay, so what is this technique will do? So we will have a formula IOU. Okay, so we'll calculate using that. So actual bounding box, so IOU formula is actual bounding box into intersection area. Okay, by union of area, union of area. So this is the formula of intersection over union, IOU. Okay, so this is calculated in the predicting bounding box. Okay, from predicting bounding box we'll get this. Okay, so we'll multiply this two and divide by union area. Okay, this is the formula. So depending upon the values, okay, so if you are getting greater than or equal to 0.5, then we classify the bounding box prediction model by, then we call them as true positive. Okay, true positive values. If the values is intersection over union value is greater than or equal to 0.5. If IOU is less than 0.5, then we'll call it as false negative. Okay, so it is similar to precision and recall matrices that we have seen in machine learning and previously. Okay, so if IOU greater than or equal to 0.5, then we call it as true positive. IOU less than 0.5, then we call as false positive. Okay, if the model is unable to predict, that means IOU is 0, then we call it as false negative. Okay, if IOU is 0, we call it as false negative. If model did not predict and it is wrong, and it should have predicted, so we can draw this conclusion if IOU is 0. Okay, so you could see how we are using it. So again we'll have mean average precision also. Okay, we will have mean average precision also, that is also one of the techniques. So we have seen IOU and that calculation, right? Then the other technique is mean average precision. Here what we'll do, so here we will identify bounding boxes are presented in the form of coordinates. Okay, okay, top, left, right, top, bottom, left, right, like this we'll identify the bounding box coordinates. Okay, so in this way I think some more steps are there to this mean average precision. So using that we can calculate this mean average precision. Okay, so that is also one of the parameter to detect how good the models are. Okay, how good the object detection is happened. Okay, whether they are detected properly or not. Okay, So next technique, mean average precision. So we can use mean average precision also to evaluate object detection. Okay, so this is the formula for that. Okay, so you can use that also. Okay, next, the most widely used metric, that is precision recall curve. So like how you have AOC, ROC curve, so here we have precision recall curve. Okay, precision recall curve for the object detection models. Okay, so how you will calculate this precision recall calculations, you could see here we having object detection models that has cats from images. So let us assume the dataset has only 4 images of cat in them. So for each of the image, the model runs a bounding box. Okay, a predicted class, a confidence score, and a predicted class. Okay, confidence score for the predicted class. So for each of the image, the model runs a bounding box, a predicted class. Okay, so model runs a bounding box and a predicted class and a confidence score for that predicted class. Okay, so these are the steps that we can follow. First, we pass the data set of image through object detection model. Then the model gives confidence score of the different images. Then we determine if image is true positive, false positive, and false negative based on IOC calculation. Then so it is extension to the IOC calculation. Okay, after calculating IOC less than 0.5, greater than or equal to 0.5, we have talked previously, right? So after that, so till here the steps are repeated. Okay, the next step, the last step, we calculate the ranked precision for the top k sorted results. Okay, so this is how we will use a precision recall curve. So we will be plotting it also. So we will perform using these formulas, we will perform calculations, and you see the curve also. The curve also looks similar to that AOC curve and ROC curve, similar to like this, if you ask me. Okay, so you can go through it. Okay, precision recall curve. Okay, so that's it. So that's it for today's session. So I hope you understood few concepts. Okay, so you have understood so what are different convolution neural network architectures like LNet5, AlexNet, VGGNet, ResNet, InceptionNet, GoogleNet, and then followed by objection detection models, two-stage detector models, single-state detector models. In two-state detector models, we have seen RCNN, fast RCNN, faster RCNN. And in single-stage object detector, we have seen YOLO. Okay, so how it is happening. So and we have seen also the matrices that are used for calculating object detection models. Okay, how far they are predicting correctly, how far they are predicting wrongly. We have seen some matrices to calculate that also. Okay, so thank you all. Thank you for giving this opportunity. Thank you once again. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.